How many 5-digit numbers exist that are not perfect cubes but have an odd number of factors? Which are not perfect cubes, that is simple to get. We know what that means. But have an odd number of factors. What does that mean? Perfect square. So how many of these numbers, 5-digit numbers, are perfect squares but not perfect cubes? And so forget about not perfect cubes. We'll come to that later on. How many perfect squares are there? What is the smallest perfect square that has 5 digits? 100 square. 100 square is 10000. So that works. What is the largest perfect square that has only 5 digits? 100 into what? 100 square is 10,000. You have to go to 100,000. So you're looking at 100 root 10. Square root of 100,000 is 100 times root 10. Root 10? 3 point. Apply that. You're going to have a calculator. So life is simpler. You can just try out a few numbers and verify that. Square root of 10. Square root of 10 is roughly pi. So 3.15 work. 3.15 is a good approximation for square root of 10. So it's roughly pi. Pi square is roughly 10. So think of it like that. So 315 square we'll have to worry about, but not any more than that. And so from 100 square to 315 square. And that's a list of numbers, the bucket list that we need to worry about for this. So 100 square to 315 square, how many numbers are there? 100 square to 315 square. Those are our perfect squares that we need to worry about. How many are there in this list? 216. Out of these 216, so our from 5-digit numbers, we're down to 216 5-digit numbers. 100 square, 101 square, 102 square, all that, up to 216 square or 315 square, 216 numbers. Within this, we have to eliminate the perfect cubes. How do we do that? So is there a number that you can eliminate straight away? Sorry? 125 square will be a perfect cube. And then 216 square will be a perfect cube. Anything else? Nothing else. 2 numbers out. That's your answer. Again, looks incredibly complicated. A bunch of small ideas here. First one, you need to know that a number that has an odd number of factors is a perfect square. So we're effectively saying 5-digit numbers, give me how many perfect squares are there which don't happen to be squares of cubes. That's all this question is. So don't worry about that are not perfect cubes part. Forget that. We'll come to that later on. We are worrying about numbers that are perfect squares. That is the starting point. The smallest perfect square is 100 square. The largest perfect square is 315 square. So 3.15 is a good approximation for square root of 10. 32 square is 1024. So 3.2 square is 10 point something. Becomes more than 10. 3.15 works. And so 3.15 is a good approximation for square root of 10. So from 100 to 315 we can go to. So it's 216 numbers sitting there. Within that, 2 are perfect cubes. Remove that. Remaining. That's your answer. And so tough question, but it's not rocket science. You will get questions like this where you have to count slowly, rigorously, maintain that. So it helps to know that square root of 10 is roughly 3.15. So you have to take 315, square that with your calculator, see whether it's less than 1 lakh. Then take 316, square that, and see if it goes more than that. You have to have a good starting point. You can't say I'll try from 220 onwards. And so that becomes a nightmare. So you need to know that anchor point. Try around 310, 320. How many 3-digit numbers are possible that when represented in base 7 and in 4, and when represented in base 6 and in 3? In base 7, it ends in 4. In base 6, it ends in 3. Okay, a lot of this has got to do with the language, and so I'm going to break this down. A number in base 7 ends with 0. What does it mean? The number is a multiple of 7. Number in base 6 ends in 0. That means a multiple of 6. A number in base 7 ends in 4. What does that mean? Sorry? When you divide by 7, remainder is 4. When you divide by 6, remainder is 3. And so this is a roundabout way of saying how many 3-digit numbers exist that when on division by 7 give a remainder 4, and on division by 6 end in a remainder 3. That's a routine question. This is just a slightly different way of asking the same question. And so now again, let's break this down. 7 you divide by and you get a remainder 4. 6 you divide by and get a remainder 3. Forget pen and paper. What is the other number we jump to from here? What can we find from here? 42. When you divide by 42, what will be the remainder? 7 by 7 remainder of 4 is just minus 3. 6 remainder of 3 is just minus 3. So 42 will again be minus 3. This is a number. When you divide by 7, you get the same remainder as when you divide by 6. Both cases minus 3. Or this number on division by 42 gives a remainder of 39. And so this number is the form 42k plus 39. Got this far, then you put pen and paper, write it as an arithmetic progression, find the number of terms, all of that. That is a more routine part. Funda here, in base 7 divided by the last digit is 4. That means the number on division by 7 gives a remainder 4. So it's a different way of saying that. On 7 you get remainder 4. On 6 you get remainder 3. That means on both you get remainder of minus 3. You divide by 7, you get remainder of minus 3. Divide by 6, you get minus 3. That means you divide by 42, you'll get minus 3. Or divided by 42, the remainder is 39. So the first 3-digit number is 84 plus 39. And then you write all those numbers and get the answer. And so I'm going to see what the exact detail is. Here, this number is the form 4, 11, 18, etc. 3, 9, 15, etc. So the number is the form 42x plus 39. Find the smallest value of x, the largest value of x that is possible for 3-digit numbers, and then we are done. And so we are asked for how many 3-digit numbers are possible. The number should be of the form 42x plus 39. The smallest value x can take is 2. That we know. Find the largest value. Take the largest 3-digit number divided by 42. See the remainder. See what will work. Near through. So you're effectively thinking of numbers in arithmetic progression with the common difference is 42. The first term is 42 into 2 plus 39. That's a sequence you're looking for. And that's a very common template. All we need to do is figure out that this is listing all numbers as a form 42k plus 39. Once you've done that, you're just walking it completely. It's a good question. It's a tough question. So take your time, get it right. What is the highest power of 12 that divides 54 factorial? That's what we're looking at. Highest power of 12 that divides 54 factorial. So what is the highest power of 12 that divides 54 factorial? Once again, I'm going to outline the approach. Those of you who know the approach, plug away, ignore what I'm saying, and then try to find the answer. Those of you who are stuck somewhere, I'm going to give the first step. How do we go about this? Right? So if we're trying to find the highest power of a prime number that divides, then life is easy. Then successive division by the prime number, you'll get to the answer. And so the question where what is the highest power of 11 that divides 54 factorial? 11, 22, 33, 44. 4 11s come there. 11 power 4, you're done. Fine, but 12 is not prime. 12 is a combination of primes. And so it's 2 square into 3. And so it's not just a combination of primes. 3 into 5 or 5 into 7, life is simpler. We just need to look at the larger prime, which is 2 square into 3. So 2 2s and a 3 give us a 12. So to find the highest power of 12 that divides this number, we need to find the highest power of 2 square that divides this number and the highest power of 3 that divides this number, and then combine those. And so find the highest power of 2 that divides the number, highest power of 3 that divides the number, get those two, see that number, and then work from there. So finding the highest power of 2 that divides 54 factorial, divide 54 by 2, keep on successively dividing, add all of that, you're done. Highest power of 3, same approach, you're done. Once you have that, then we'll worry about 54 factorial back again when you're thinking about 12. And so key point here, you're looking at 12, you have to go look, let me find 2 and 3 first. Then we'll come to 12. 2 square into 3 is 12. Let's find the answer for highest power of 2 that divides 54 factorial, highest power of 3 that divides 54 factorial, see both of them, and then go to 12. Highest power of 2 that divides 54 factorial? It is 50. Fine. So 27 plus 13 plus 6 plus 3 plus 1. Fine. So successive division by 2. 54 by 2 is 27. 27 by 2 is 13. By 2 is 6. By plus 3 plus 1. Highest power of 3 that divides 54 factorial? 18 plus 9 plus 3 plus 1. So this number is a multiple of 2 power 50 and 3 power 26. What is the highest power of 12 that will divide this? Give me the answer. What's the highest power of 12? 25. So this number is a multiple of, I'm going to write this down, is a multiple of 2 power 50 and 3 power 26. Sorry, this is 2 power 50. I'm going to write it again. 2 power 50. 2 power 50 into 3 power 26. You want to see 2 square into 3, how many times this will fit. We have 2 power 50 available. So you can accommodate maximum 25 2 squares into this. So we have a 26th 3 available, but that's not good enough. The highest power of 12 that will divide this number is 12 power 25. And so 12 is a very interesting number because 12 is 2 square into 3. Sometimes you'll run out of 2s, sometimes you'll run out of 3s. So if you're doing this question for saying what is the highest power of 12 that will divide 50 factorial, in that instance you'll run out of 3s. There'll be more 2s available, more 2 squares available than 3s. For 54 factorial, there are more 3s available than 2 squares. So it keeps shifting. So some numbers it is very easy to know what you have to count. For 12, you'll never know. You'll have to find the actual number and then simplify. So find the highest power of 2 that divides the number, highest power of 3 that divides the number, then put them together. You cannot eliminate one or the other. In some cases, you'll run out of 2s. In some cases, you'll run out of 3s. So find both and then simplify that. This again we've done 5-digit numbers that leave remainder of 2 on division by 3, 3 on division by 4, 4 on division by 5, 5 on division by 6, 6 on division by 7. We've done this question without that last bit for 4-digit numbers. And so we treat the remainder as -1 and then simplify. So I'm going to skip this one, try the next one. Once again, a very standard template, x power 4 plus ax cube plus bx square plus d. So multiple of x minus 1 leaves a remainder of 2 on division by x plus 1. If a equals b plus 1, find d. What idea are we using here? Polynomial remainder theorem. When p of x is divided by x minus a, remainder is p of a. So this number is a multiple of x minus 1. What does it mean? P of 1 is 0. So P of 1 is 0, P of minus 1 is 2, A equals B plus 1, 3 equations, plug it in, you'll be able to find A, B, and D. And a very routine question, if you know that funda, these kind of questions are very common. When you look at the question, you'll know the method, you'll still have to diligently solve it and get to the answer. Very common. 10 to 12 questions will be like this. You read the question, you'll know the method. After that, you're just plugging in and solving. You'll do it carefully, rigorously, all that, but doable. You should definitely nail questions like these. And so straight away, you'll get a plus b plus d plus 1 is 0. And we'll get a plus d equals 1 plus b. Which gives us, what should be d? A plus b plus d is minus 1. Simplify this, solve for d. Again, I'm not going to go over the algebraic part. That part is doable. I don't want to spend time solving 3 equations and finding the answer. Answer is d equal to 2. Just plugging in polynomial remainder theorem. Nothing more than that. We'll go to the next one. Two-digit number multiplied with a number formed by reversing its digits is 3640. Answer? 11. 56 into 65. And so all of these questions, if you prime factorize it, it becomes very simple. So if you prime factorize, we get 2 cube into 5 into 13 into 7. If you have a 2 and 5 in the same box, that gives us a 0. So the number will end in 0. So that's impossible. So 2 cube has to be in one number, 5 has to be in the other number. One number is a multiple of 8, the other number is a multiple of 5. An odd multiple of 5. An even multiple of 5 will end in a 0. So take all 2's, put it into one box, remaining put it in the other box. So it's either 2 cube into 13 into 5 into 7, or 2 cube into 7 into 5 into 13. One of those is the answer. 2 cube into 7, 5 into 13, that works. 56 into 65. 52 into that larger number, 105, doesn't work. It becomes a 3-digit number. 56 into 65 works. So again, it's a typical question, very doable question. You should nail it. These are the kind of questions where you not only solve it, but try to solve it with time to spare. Very formulaic question. Plug in n into n plus 1 by 2. Find this become 1007 into 2015. So 1007 by 48, find the remainder. 2015 by 48, find the remainder. What are the reminders? Minus 1. So minus 1 into minus 1, 1. Done. Fine. So n into n plus 1 by 2, plug in the formula. This answer is 1007 into 2015. Both leave 1007 division by 48 gives a remainder minus 1. 2015 by 48 gives a remainder minus 1. Minus 1 to minus 1 plus 1. Very simple, very routine question. You will get questions like this, which you just nail straight away. Please don't multiply 47 and 47 and get a big answer. Divide that by 48 and find the remainder. If you can think of 47 as a remainder as minus 1, life is far simpler. But it's minus 1 into minus 1, which is plus 1. This one's slightly tougher. Give it a go. We'll discuss this. One of those questions where if you list down a few numbers, you can see some pattern coming through. You don't need to do it algebraically. So solving for n into n plus 1 by 2 equal to 9k plus 1 is tougher. N into n plus 1 by 2 is at the form 9k plus 1, and then solving that algebraically, that's trickier. Whereas if you just list down the numbers, you can see if some pattern comes through. And so I'm adding number 1, 1 plus 2, 1 plus 2 plus 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, etc., 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 etc. So which numbers on this list leave a remainder on division by 9? 1, 10, 28, 55, 91, and so on. Is there a pattern? Sorry, every third number. Fourth number, seventh number, 10th number, every third number. First, fourth, 7th, 10th, 13th, all of those work. So every third number on this list work, starting from 1. So 1, 4, 7, 10, 13, 16, 19, 22, all the way till 97. So how many ever numbers are there? That's your answer. So now let's think about why that works. And 1 is just 1. That works. And 1 plus 2 plus 3 plus 4 is 1 plus 2 plus 3 plus 4. 2, 3, 4 added is 3 times 3, 9. That's a multiple of 9. 5, 6, 7 added is 3 times 6. That's a multiple of 9. 8, 9, 10 added is 3 times 9. That's a multiple of 9. So to 1, if you add 2, 3, 4, 2, 3, 4 is a multiple of 9. 1 leaves a remainder 1 on division by 9. 1 plus 2, 3, 4 gives the same remainder. Plus 5, 6, 7, plus 8, 9, 10, plus 11, 12, 13. Remainder is not going to change. If continuously I'm adding in sets of 3. 2, 3, 4, 5, 6, 7, 8, 9, 10. They're all multiples of 9. So if 1 works, to that number adding any set of 3 will keep on working. 1 leaves a remainder 1 on division by 9. Therefore, n could be 1, 4, 7, 10, 13, 16, 19, 22, 25, all the way till 97. We told n is less than 100. N can't be 100. So 1 all the way till 97. So 33 different numbers are possible. And so n into n plus 1 by 2 equals 9k plus 1. And then solving that algebraically. That also works. That's far tougher. And plugging in a few numbers, seeing a pattern, and then taking a chance, that works far better. Here, just doing nothing, forgetting about this 9 thing, writing down what could be the value or sum up to n numbers for 10, 12, 13 numbers. So 1, 3, 6, 10, 15, 21. If you see that, every third number in that list works. 1, 10, 28, 55, 91, all of these work. Every third number works for us. So we're good. So you're looking at n equal to 1, 4, 7, 10, and so on. Whichever till 97, count that, and then we're good. Try this. Good question. Again, a typical question. Give it a go. again the question for which you don't need any theory, don't need anything about reminders or digits or nothing. Assume a number, plug in, find R, K, P, see what fits, then see the pattern. And so don't assume a number which is very symmetric. Don't assume the number to be 500 or 333 or 444. Then you're not able to distinguish between one and the other. Assume some number like 1568 and then try out these things. Plug in R, K, and P and see what works. Then you can see the pattern, what will work, what will not work. And so make sure that your original starting point assumption is reasonably general. It's not a special number. It will satisfy a bunch of properties because it's symmetric. So ignore that category of numbers. Assume a general number, plug it in, and then find R, P, K, and then verify which of these properties works. Should we discuss this one? And so, a number and division by 10 leaves a remainder R. That means the last digit. Division by 100 leaves a remainder K, last 2 digits. Division by 1000 leaves a remainder P, last 3 digits. Which of the following are true? The 10th digit of this number is K minus 10R. True? Yes? If you take the number to be 1568, R is 8, K is 68, P is 568. So K minus 10R, 68 minus 80, that's minus 12. That's not the unit digit. That's not the 10th digit. What should be the 10th digit in terms of R, K, and P? K minus R by 10. K minus R will give you a multiple of 10. Divide that by 10. That will be your 10th digit. K minus R whole divided by 10. That's your 10th digit, not K minus 10R. The 100th digit of this number will be P minus K by 100. So from the last 3 digits, subtract the last 2 digits. That means you'll get a multiple of 100 followed by, basically the 100th digit followed by 2 zeros divided by 100. That is true. Statement B is true. The remainder when the number is divided by 50 should be K minus 50. This is true. In this number 1568 it works. 68 minus 50 works. But if the number were 1518, on division by 100 remainder will be 18. On division by 50 also remainder will be 18. The number ends in 2 zeros. The remainder is 0. By 50 also the remainder will be 0, not minus 50. So it cannot be K minus 50 always. Some cases it is, some cases it is not. The only statement that's always true is statement B. A need not be true, C need not be true. Try this one. How many 2-digit numbers AB exist such that AB and BA are both prime? The 2-digit number AB is prime, so is the 2-digit number BA. Again, nothing but a trial and error question. Do this diligently. Very possible that you'll get a question like this. And so, got to be smart about this. What are the starting points here? What do we know about A and B? Two-digit numbers. Both should be odd. That we know. Otherwise, one of the numbers will become an even number. And what else? So we are dealing with digits 1, 3, 5, 7, 9. Within this, what are we not dealing with? What? You don't need to worry about 5. We're dealing with only digits 1, 3, 7, and 9. So think about 1, 3, 1, 7, 1, 9, 3, 7, 3, 9, 7, 9. You're done. And then flip those. So limit what you're considering. So 1, 3 and 3, 1. 1, 7 and 7, 1. 1, 9 and 9, 1. Then 3, 7 and 7, 3. 3, 9 and 9, 3. 7, 9 and 9, 7. That's all. It can be 1, 1 also. Finally, I was about to come to that and say it can be 1, 1 also. So finally, you have to worry about 1, 1. So 1, 1 is a possibility. If you're given a question where it is A, B, it is not built in that A and B are distinct. That has to be explicitly stated. You're told that your two-digit number of the form AB where A not equal to B, A and B are different, A and B are distinct with two distinct digits. Unless otherwise the distinct part is explicitly stated, it cannot be taken for granted. Two-digit number AB, A could very well be equal to B. So 1, 1 is still a possibility. None of the others are possibilities because they'll all be multiples of 11. But to all the possibilities you count like this, you have to add that number 11. Don't forget that. A very routine question, but it helps to simplify. You should straight away say no even numbers, no even digits. You should straight away say no 5. I'm dealing with only 1, 3, 7, and 9. And then go step by step. 1, 3, 1, 7, 1, 9, 3, 7, 3, 9, 7, 9. And then flip all of these and find which ones are prime both ways. So do it methodically so that you don't miss something, but limit your possibilities very early so that you're dealing with only say 5, 6 numbers. And then don't forget 1, 1. How many numbers are possible? 4 pairs or 4 numbers? 4 pairs and 1, 1. 9 numbers are possible. How many numbers possible? 9 numbers are possible. 1, 1, 1, 3 and 3, 1, 1, 7 and 7, 1, 3, 7 and 7, 3, 7, 9 and 9, 7. And so 9 different two-digit numbers are possible. 1, 1, same. 13 and 31, 17 and 71, 37 and 73, and then you have 79 and 97. So there are 9 two-digit numbers that satisfy this criteria. No rocket science, no method, just listing down, but listing down carefully. Forget even numbers, forget 5. Don't forget 11. That's what we need to keep in mind. Very good question. Give it a go. Again, a typical question. You don't need Bhayankar theory, but it's a roundabout way of asking for a different question, different number. So give this a go. We'll discuss this. Ten less than n less than 100 such that n is not a factor of n minus 1 factorial. So, and we want a number n which is not a factor of n minus 1 factorial. Is 15 a factor of 14 factorial? 20 a factor of 19 factorial? When will a number n not be a factor of n minus 1 factorial? Effectively, this is saying how many two-digit prime numbers are there. Less than 100, how many primes? Two-digit primes? 21. Roundabout way of asking how many 2-digit prime numbers exist. It's a very common question where it's just one idea, you just spun it around slightly differently, just trying to throw us off our game. Done. So how many 2-digit prime numbers exist? That's all this question is. Nothing more than that. Any number n can be factorized as sum a into b if it is not prime. So both a and b will be less than n. So they will feature when you write from 1 into 2 into 3 into all the way to n minus 1 factorial. A and b both will feature. So only way n is not a factor of n minus 1 factorial is if n is a prime. And so we're effectively saying 10 less than n less than 100, find all prime numbers. This again is a typical question, slightly tougher than the previous one. Get the funda and then go about it methodically. We've discussed questions like this. So it's very similar to one or two questions that we have discussed. You divide a number by 7, you get a remainder. Divided by 9, you get a remainder. How many 3-digit numbers are possible? It's just a variant of that question. Right. What is the remainder when 4444? So many 2014 times. Obviously, this year it will be 2017 times. Right. So that apart, this number divided by 72, what is the remainder? Right there. So you have 4444 appearing 2014 times. We divide this by 72. We need to find the remainder. I'm not going to give the answer. I'm just going to give the starting step. What do we do? Those of you who found that out, carry on and solve that. We need to find the remainder when we divide this by 72. And so obviously finding by 72, dividing this is incredibly tough. So how do we break that? By 9 and 8. Divide this number by 9, find the remainder. Divide this number by 8, find the remainder. And then we'll worry about combining that. Right? How do you find remainder when this number is divided by 9? Sum of all the digits, divide that by 9. That's your answer. If that is too big, add the digits of that number, divide that by 9. That's the answer. So 4444 2014 times, add 4 2014 times, find that number. If that is also a 4-digit number, add all those digits. Keep on adding digits till you get a number. That's a remainder when you divide this by 9. Finding remainder when you divide by 9 is nothing but continuously adding the digits relentlessly till you get a number from 1 to 9. That's it. Nothing more than that. So how do you find the remainder when this number is divided by 8? Last 3 digits. So 444 divided by 8. Whatever that remainder is, that's a remainder when this number is divided by 8. So find remainder on division by 9, remainder on division by 8. Keep both of those. So you should be able to write this number as 9k plus something, 8p plus something. And then we combine those two to get 72l plus something. That will come to later on. Starting point is to say 72, 8 into 9. Let me find on division by 8. Let me find on division by 9. And then I'll worry about the rest later on. Right? On division by 8, what's the remainder? So this number is of the form 8k plus 4 that we know. On division by 9, so the form 9l plus 1. So once we have that, good. So it's the form 9l plus 1 and 8k plus 4. Write this down. 9L plus 1, 8K plus 4. Got this far, but we want to divide this by 72 and find the remainder. So we're not worried about 9 and 8, we're worried about 72. So if the number leaves a remainder 4 on division by 8, then on division by 72, it could be 4 or 12 or 20 or 28 or 36, 44, 52, 60, 68. If it leaves a remainder 1 on division by 9, it could be 1, 10, 19, 28, 37, 40, 46, and so on. One of these numbers is common to both lists. That number is 28. And so our number of the form 72K plus 28, or 4444 2014 times divided by 72 gives a remainder 28. So, yeah, sure. There will be only one number. As long as 8 and 9 are co-prime, which they are, and dividing by 72, there will be only one number. And so if you're by chance trying to use 8 and 6 to find by 48, there will be two possible answers. LCM of 8 and 6 is 24. So that will tell you, look, there's something funny happening, then you'll have to come back. So I'm going to stop with that. The last question is fairly simple. Give it a go. You will get the right answer. I'm confident. So I'm going to wind up for the number systems. So we'll have a session on verbal reasoning an hour and a half from now. Tomorrow we'll do geometry and then kind of spill over to mock CAT discussion, panel discussion, and the rest of it. And so any questions, doubts on number systems, now is the time. What to prepare for in number systems, focus a lot on prime factorization, number of factors, HCF, LCM, that end of it. The really simple 7 standard, 8 standard end of it. And keep your wits with you. Quite a few questions in number system. Like in this sheet, at least 4 or 5 questions could have been done with no theory, where you're just trying a number, substituting a value, being street smart and getting the answer. You will get quite a few questions on number systems like that. So don't get caught up in the algebra. Like that question where 2-digit number and product of a 2-digit number AB into BA is 3640. If you wrote that as 10A plus B into 10B plus A, that's a wild goose chase. But if you do trial and error, you're hitting the answer straight away. And a great many questions will start with prime factorization and then putting it into some boxes and some patterns. And so don't get consumed by the algebraic end of it. So be very careful of overdoing the algebra part in number system, and don't do too much of reminders. Reminders don't get tested. The simple end of reminders get tested, but 7 power 7 power 7 power 7 divided by 48 ain't happening. And so don't do an overkill on reminders. Know the basics, leave it at that. Factors, factorials, HCF, LCM, the street smart type of questions, prime numbers, composite numbers, those are important. Right? Super guys, thank you. All the best. We'll circle back by a little before 2 o'clock, 1:55.